Hello, everyone, and welcome to Ask an ITASCA Consultant. This is the first of a series of webinars that we plan to host. Today, we have Augusto Lucarelli, Principal Engineer. He has a background in soil mechanics, numerical modeling of geotechnical processes, shallow and deep foundation design, soil improvement, slope stability, mechanized excavation, conventional tunneling in urban areas, deep excavation, and support structures in difficult environments. He has a numerical software experience using FLAC, FLAC3D, UDEC, Plaxis 2D, Plaxis 3D Foundations, Plaxis 3D Tunnel, Excel and Excel VBA programming, and AutoCAD. So the intent of today's webinar is we had people submit questions if they had any as part of the registration. So we have a few questions, and Augusto will be addressing those. If we have time at the end of the webinar presentation, we will open up the floor for general questions and answers or follow-up questions. If you want to submit a question, please use the Q&A icon at the top of the Teams application, or feel free also just to use the chat. This video will be recorded and it will be posted to our YouTube channel.
Well, welcome everyone. Again, this is an initial experiment. Let's see how it goes. And as I was mentioning in one of the LinkedIn posting, it is supposed to be more of a exchange of idea conversation without getting too deep into the weed of any specific items, because otherwise it would become a lecture of some sort. We receive a few questions that are very interesting and kind of provide, I would say, there is a common theme that I see looking at this question. So I'm trying to focus, instead of going into 25 different directions, I will try to focus on three main items that are kind of coming from the first question and the second questions, which are mostly related to the parameter and constitutive model selection. How do you handle the uncertainties, and what do you do if you don't have data, and whatnot. The second one is also very interesting, related to the plastic hardening constitutive model, and how would you handle strain softening, because the current formulation doesn't have strain softening included. And finally, this is a common theme for the third one, is a never-ending question, always present in any circumstance. Coupling spring, L pile, PY curve, and what is the coupling spring meaning? How do you use it? What is the calibration and whatnot? So we have only 1 hour, and at least just to cover one of these topics, it could take at least probably 2 hours. So let's get started. Let's go and the first item is that numerical modeling, it is a tool in our toolbox, okay? It's not the end-all, be-all, and it needs to, but it is a very powerful tool if you know what you're doing. Meaning that even if you don't have all the details or all the information that you think you need to run a numerical model, it provides I would say, a way to tackle the issues, and it becomes a sort of a numerical lab in which you can test idea, you can test sensitivity to parameter and stuff like that. And the reason for doing that, and you can do that even with closed form solution, of course, right? You can take a Brink-Johnson formula, you can plug in a friction angle, and you come up with different type of bearing capacity, for example, or a settlement analysis and whatnot. But the advantage of the numerical modeling is that it captures much better the physics and the mechanics of the whole system. This is more important when you have a complex system. For example, you have ground improvement, then you have reinforced soil, then you have soft clay, and a bunch of different systems that they interact using or mobilizing different level of strains during the interaction and during the problem that we are trying to solve, for a deep excavation or a TBM or an embankment in soft clay and whatnot. So in order to be able to combine and to try to understand where is the weak links, or where are the weak links in our system. Numerical analysis provide an unparalleled tool to evaluate those risks. And also this becomes very important in terms of two main reasons, in my view and in my experience. One is potential optimizations. My experience, what I've seen, when you adopt very simplistic approaches, you tend to be overly conservative. This is one, and when you work for contractors, that is something that could be not desirable. The other item is that you may mismanage risk, because if the system that you're adopting for the analysis is not adequate enough to capture at least some of the major complexities that are inherent in the system that we are analyzing, you don't really know what's going on. You don't know if the pile is going to fail first, or is the soil that is going to fail first. Is the geogrid mobilizing enough strength to provide an adequate performance expectation for the MSE walls and whatnot? I'm throwing out examples just to give you an idea about how you should be thinking, or I mean, I wouldn't say how you should be thinking. The way I use numerical modeling and how I think about the application of numerical modeling to solve real problems. So one example for all, and I take let's say the first point is the question here. The third bullet point, the first question is, what is the recommended workflow to determine model parameter when laboratory data are limited? Okay, I never use laboratory data, so either they are a lot or limited. It doesn't really matter. The main reason is that there are very few soils that are providing reliable data from lab measurements. You take the London clay, you take the Boston blue clay, the Bay mud, the Vatican clay, or some other region in which, and you know, there is a common theme between these different units, clay. Right, so it is relatively easy to sample, and it provides a decent. So the lab activity provides a decent measurement of the parameter that we need. But in general, the vast majority of the lab activity that I've seen are not good enough to be used for calibration or determine, let's say, numerical modeling parameter. So the way that I use, I tend to rely mostly on in situ test, and specifically when it's possible, cone penetration test. In my opinion, when you have those kind of soil, the cone penetration test is an invaluable tool to evaluate the interference or the interaction between different layers of different permeability, different consistency. So you can better estimate the time scale. You can better estimate the response of the soil at the scale, at the larger scale. The lab test is very narrow, is very limited. That you cannot really consider any kind of spatial variability in any way, shape, or form. Even the old SPT, for example, when the CPTs is not available because you have a stiff granular soil and stuff, even the SPT on its own can provide a good hint in terms of soil variability and in terms of distribution of property around the site. Okay, then you can plug in some sensitivity analysis in terms of what do you correlate to the SPT in terms of BS, for example, or friction angle and whatnot. So in order to provide a little bit more specific example, I'm going to show you an application. And this is the way that I use, for example, the calibration of the plastic hardening for solving any kind of problem. Okay. So in this case, the way I use the plastic hardening is I tend to use the CPTs, and you can see here an example of CPTs in which I obtain the solid behavioral type from Robertson, and then you can plug in all the correlation that you want as a function of CPT. And the idea is to actually feed the model without chasing these layers that you have here and here, but just providing the distribution with the vertical with depth of the specific properties that you want to implement. For example, I use an extra variable. I'm not going to get into the detail of what an extra variable is. It's just a store in which I put my quantity that I need to use. For example, you see this formula here. I put those into a store in the model, in the memory in the computer, so that I can use those to calibrate, for example, and to use other parameter. For example, the same is for the GMAX that I can obtain from CPTs, and I give the GMAX as a distribution, as a table, as a function of depth. And so once I have the GMAX in mind, or other properties like the solid behavioral type, I determine the main parameter of the plastic hardening model using this idea here. I'm gonna switch. Using this example, for example, here this is a very weak soil with a lot. You see the CPT is here. There is a lot of intercalation with sand and then clay and whatnot, and then there are some settlements, measurements that have been performed on site. And so the basic idea, without getting too much into the detail, is take the CPTs, come up with profile of the property that you need. For example, in this case, density and porosity. Then you have the GMAX. Then you have the solid behavioral type. Then you can plot also the odometer, for example. You can give any type of property that you want, including, for example, the coefficient of consolidation in case you want to analyze settlements with time and so on and so forth. And then how do you, let's say, reconcile all this property that you give into the model with the plastic hardening property that the plastic hardening model needs? The plastic hardening model essentially needs the Emax, and I'm talking about the small strain, right? Then it needs the E50, the unloading, reloading, the odometer, and some other parameter like the alpha, the M, and so on and so forth, the ratio, the failure ratio, and so on and so forth. The idea that I use is not to focus on the reference parameters. So typically, this is the formula, and this is valid for any type of parameter. I don't try to use the reference. I actually determine, for example, the unloading, reloading from the Emax distribution that I get from the shear wave velocity, and from that Emax, I apply a divisor to or a factor to obtain one of the parameters, so that I have distribution of the E50 or the unloading, reloading with depth, and then I reverse the formula and give to each zone of the model the reference value, because the formulation is in terms of reference, but the E-reference, whatever that is not a physical properties. It is a numerical parameter. The real physical modules or quantity is the 50, is the unloading, reloading, is the odometer. And so once you have that as a function of depth, and you know the stress that you have in the zone, then it's easy to reverse the E50 reference. And I have applied this methodology for decades, and a very good success in even in the design phase, when you don't know what is going to be the performance. But if applying this strategy, it gives you a very good, I would say, connection with the soil distribution and the expectation of this property on the site. And then when you go at the end of construction, then you have the monitor system that provides you some feedback. I've seen decent, in some cases remarkable, but all in all, let's say between 20, maximum plus minus 20% in terms of settlement, and in some cases very, very close. Another item that I take into account is that these factors that I apply to determine the E50 or the loading are typically a function of the soil behavioral type. I'm not going to get into how to determine this function, but essentially these factors tend to be, if you are in a sand, those factors are close to 1, and then they tend to become lower if you have, if you tend to migrate into the clay all the way up to the zeros, all the way down to 0.5, 0.6. So there is a transition zone in which there may be some gray area, but even taking a straight line, it is a decent initial approximation. As far as the alpha is concerned, there are some indication that you can extract from this paper from Paul Main. I typically use a value between 0.75, 0.8 as a general value. And then as far as M, also there is some indication in the Zeta Soil manual that allows to determine. So this is the background on how to select. As you have seen, even for this project, I had tons of lab data, tons. I just didn't look at all. Beside the physical properties, the value of the lab data is the physical property. For example, the measure of the density, the measure of the void ratio, the upper limits, so physical quantity that are useful in term of soil characterization or classification, I would say. But as far as the mechanical parameter, I would say they are a little bit better for the shear strength, but when it comes to the deformability, especially at scale, the lab data are, in my experience, essentially not applicable. This is, for example, just to go into a detail, a real project. This was a very large project for the TPI in Duluth, in which I applied this methodology to evaluate the foundation and ground improvement of this large project. These were over 10,000 columns for ground improvement, and all the characterization soil was done in this way. And then we also had a field test. I'm not going to be able to go into the detail. I'm just going into the calibration of the plastic hardening here and to the results that I want to show. This is another interesting example. At the end of the day, what we were able to achieve is for them, because here the main topic was to evaluate the settlements of this big embankment here, and what we were able to achieve using this strategy, this calibration. Also in this case, there were a lot of lab activity, but none of the lab data were used to calibrate the pH model. All was done with CPTs and a little bit of the field test, but mostly with the CPTs. And we got an amazing results in terms of, you see the maximum settlement was 12 centimeter, 120 millimeter, and all the extensometer that we put and the SSA, the horizontal SSA, confirm this data. Just because I'm in this presentation, it kind of come to my mind another interesting application that is relating to my introduction about soil structural interaction. And when you have complex system, the value of doing numerical analysis. For example, this is a typical case in which you have ground improvement because we have a very soft, poor soil. And we have an RSS, a reinforced soil slope, with geogrids. And the debate is, what are we going to do in front of this? Is it better to put more columns? Is this going to be enough to control the shear failure? You see that there is a significant mobilization here of these columns on the side, at the edge of the embankment. The reason is that because, of course, we have the lateral force there, but also because the columns per se, these are concrete, non-reinforced columns, but even if they're reinforced, when you don't have axial force, they don't have much of a bending capacity anyway. So these columns that are here are not really helping to improve the performance of the embankment. While if you plug in, for example, a limit equilibrium and you do just a force analysis, considering the full mobilization of the shear force of this column, you might get a satisfactory number. But there are two problems with that approach. One, the shear capacity of the columns neglect most of the time the bending. So the bending brings the columns to failure first, then in shear. And second, the strain compatibility in this system is totally neglected when you go with a limit equilibrium type of analysis. A column can tolerate just maybe a few fractional percentage of strain. Geogrid deform all the way up to 10%. So how can you reconcile this different order of magnitude difference in strain, and then you assume that everything is mobilized at failure? And so that is the advantage of using numerical analysis in this type of application. And without you see here how these columns are bending. At the end of the day, you see the concentration of strain, and the column is bending in this case. At the end of the day, the best solution was to eliminate those columns at the side and put a reinforcement inside the embankment. I'm going to keep going and explore other topic. How do you handle parameter uncertainty in consulting practice? There isn't a single answer. We are always, no matter how many data you will have, there will always be uncertainties. At the end of the day, you have to use the tools in your toolbox to gain confidence on what is the probability, the expected probability of the outcome that you are designing, and focus on what is the impact of those uncertainty in the performance of the system. We need to shift, I would say, our mindset toward performance analysis and not just factor safety per se. Factor safety per se is very limited. It doesn't tell the story. Most of the time, you get into a litigation not because the factor of safety was 1.27, but because the embankment moved, several inches, and the structure went out of service. What was the factor of safety in this case? Nobody knows, but the performance is visible. Okay, so that's the paradigm shift, and there is no, again, single answer that would satisfy everyone. At the end of the day, you have to gain confidence based on experience and do several tests and see what are the uncertainties that you can reduce. Doing sensitivity analysis. How do you bridge the gap between sophisticated numerical analysis results? I think that I already talked about this. I don't think that there is a gap to bridge. There is a tool or a series of tools that allow you to understand how the system behaves. That is our goal. Okay, the goal here is not to match a Boussinesq stress distribution with a numerical analysis for the foundation. Boussinesq distribution is an elastic condition. It doesn't take into account K-note. It doesn't take the effect of different layer of stiffness, and so on and so on. I'm just bringing up an example just to give something that we can all relate, right? So at the end of the day, what we are trying to do here, I don't really need to match a Brink-Johnson bearing capacity. I don't need to match, the P zeta the PY curve that is coming from Rees or anybody else. I need to understand how the system performs and behave. That is our scope. So I don't need to reconcile anything. Once I'm confident in the approach and I manage the uncertainty to tolerable value, then I'm okay with that. I think this last one I already walked through several examples in which I use how I use the data and I'll build the numerical model and how you select the properties. But again, I'm not looking to say, hey, I've done a numerical analysis. I get this value. Oh my God, I need to check with this Excel spreadsheet to see if I get the same value. No, I don't care. I need to use some kind of a settlement analysis based on Boosetnik's theory to see if I get the same value. No, I just don't do that. To me, the primary tool for design, not only for design, but again, even before design, to understand the mechanics and the physics of the system is numerical analysis. There is no other way to do it. And I think that the world is moving very, very fast, finally, toward that direction, hopefully. Okay, so when it comes to the first two questions, I cannot really speak about that. I will only mention for several reasons. We have NDAs, non-disclosure agreement, and we cannot really talk. We have several litigation, and we cannot really talk about those things. And also because before the NPM, do runoff analysis was not that easy. Either you have, for example, in FLAC3D, there was the remeshing tool that would allow you to do, let's say, the progression, to follow the progression of the initial geometry toward a final configuration. And so you may have been able to develop some sort of information about the runoff. In 3D, there was nothing. Or you would need to go and adopt a DEM. The problem with the DEM is that it's much more intensive in terms of computational effort, much more demanding, and so it has been rarely used. Now, finally, with the next version of FLAC3D, the 9.8, is already available in beta testing in 9.7, but we officially releasing the next one. We have this material point method, which essentially overlays into the zones the concept of the material point methods that allow to essentially accommodate large strain and update the stress and strain field using the zones as a background, so that you can follow the progression of the mesh and how that it deforms during the analysis. The beauty of this approach is that you don't really need to specify properties specifically for the NPM. The NPM reads the property directly from the zone. So you set up a model in FLAC3D like you would do with FLAC3D normally. You, for example, you select a plastic hardening, you give the property of plastic hardening or more Coulomb, you give the property of more Coulomb, you let the model go into equilibrium, and at some point you trigger the NPM and you do your runoff analysis, or you do your large strain analysis, and so on and so forth. So it facilitates I would say, the mesh generation, which is similar, which is example the same as it was before. The NPM generation with a few parameters is automatically organized and executed inside the FLAC3D engine. And the properties, you just need to specify the property that you would give to FLAC3D constitutive model anyway, and NPM read those as a main property for the rest of the analysis. I hope this out to have a little bit of a better idea. Now, let's go to the second one, because this is also a common theme. I've been in this situation myself multiple times, and I'm going to show you one example that I used to inject the strain softening behavior into the plastic hardening. As we know, the plastic hardening soil essentially exhibit hardening until it intercepts a failure, and then it goes flat. In many cases, I would say in a significant amount of cases, we have test or lab data that are showing this type of behavior. You tend to have this is in Boston. This is you have a peak, and then depending on the confinement and other property, you have a decay of the properties somehow. So what I develop. This is the common framework of the plastic hardening, which this is the let's say equivalent, I would say equivalent more Coulomb that goes into the 50% of the failure, and this is the asymptote that you add at some point. And these are the difference between the annual loading, reloading, DN50 and whatnot. And then in case you have a distribution like this, what I did, I developed a strain control plastic hardening model in which each zone checks what is the strain level, and if depending on the strain level, update the shear strength properties so that it can actually follow somehow the softening behavior. Right, and also this one can accommodate nonlinear strength envelope. This is another topic that is not in the question, but is strongly related to this aspect. We tend to characterize the more Coulomb model with just cohesion and friction angles, so sort of a linear envelope. But the effect of the nonlinear strength envelope, I would say, in any type of soil, some more, some less, it is critical. It is crucial to have a better understanding of the mobilization of the shear strength, the volume of the soil that is pushing against our structure, and so the overall performance and behavior of the system. So what I'm saying is that it is possible, I've done it myself, to include strain softening into the frame of the plastic hardening. And it can be done, again, controlling the shear strain. Once you go over the peak shear strain or the peak axial strain, depending if you're looking at the Q or if you're looking at sigma 1, that is equivalent, is the same thing. Then you can degrade the shear strength following a certain, I would say, strain degradation curve, like you have it here in the lab. So here I was trying to mimic based on different lab data that I had for this triaxial test, just to show some example on how the system behavior. And again, even this lab activity is a tool essentially that is still related on shear wave velocity to determine all the stiffness, and then in nonlinear strength envelope, the typical nonlinear strength envelope, the power law, in which we have the A and B to determine the shear strength of the material. Going back to the question, so we can accommodate large strain softening in the plastic hardening. This module is not commercial available right now, is something that I have for my own consulting. At some point, maybe we would develop it and make it publicly available. Although I have to, specify that this is for static. Okay, your question here for dynamic analysis, and for that dynamic analysis, I would agree with you that it is questionable unless you're a relatively small strain. To be able to capture the degradation is still used if you have material that can exhibit, I would say, hardening all the way up to maybe 5-6%. You probably just need to check that the strain during cycling doesn't really go above that level. So it is a sort of a more combination of running the analysis with the tool that we have, because it's still better than doing nothing, but use some engineering judgment, like I'm sure that everybody does, on top of the result that you're getting. Yeah, so I see this that the time history could become more relevant. Yeah, the degradation. If you have a material like a hard clay that after 1% of strain degrade to 50% shear strain, then you might be in trouble. You can come up with some kind of trick. Taking, I don't know, 50% or 75% of the shear strain, but essentially, it could be a poor hack because the constitutive model is not designed to capture that type of behavior. But in static condition, as I shown earlier, it can be done, and you can also take the loading, unloading, and reverse, and go back to the original reduced strength. And so that in static condition is fine. I never tested and used it. It might work even in dynamic, but I never tested and used it in dynamic. I've used the traditional, I would say, the standard formulation of the plastic hardening in dynamic, when there is no liquefaction. If there is liquefaction involved, I wouldn't use it. There are more elaborate, specific models for capturing the liquefaction triggering and also the post-liquefaction aspect, like the P2P sand or the North sand and similar. Now the fun one. We have about 20 minutes left, or 15 minutes. There may be some conversation. This is the team that every time, even in support, we get consistently. What are these coupling springs? When you set up a pile, or for example, a liner, there is the need to give properties to this Kn, Ks. Let's talk about the pile, and let me bring up an example here so that everybody has in mind. Okay, this is just a cartoon, okay, about what we're talking about. So this is our domain of analysis. This is our pile element. This is an embedded element, so it's volumeless. It's based on the beam theory. It could be elastic or nonlinear. And now we have also the possibility to model this pile as a concrete element. So this is just a parenthesis. And then in these nodes, we have to connect essentially the pile with the zones, with the domain. And these links, this connection creates so much confusion that is unbelievable to a certain extent, because it's very simple. These are not PY curve, okay? When we use LPile or any kind of program of that sort, the soil is not present. The PY curve or the T zeta curve is essentially the soil, right? It simulates the interaction with our structure, with the soil, and everything that comes from the soil is essentially lumped into the coupling spring, right? So if you have a sand, you have a certain formulation that trees develop. If it is a clay, a hard clay, or soft clay, there are different shapes and stuff like that that can be used to determine what kind of PY curve you need to use for those type of analysis. That is one approach. In this case, the soil is modeled explicitly via zones, in which you have a constitutive model, you have the property, the soil is deformable. The effect of these links, either horizontal or vertical, and we're going to make a distinction between the two, but because there is an important distinction, is just a way to transfer the forces between the node of the structure and the zones that represents the soil. So what I read there in the question, the idea of fixing the soil and just pushing the pile and calibrate those links is essentially wrong. And this is why. Because if you calibrate the links to match the behavior that you want in mind to replicate the PY curve, when you relax the soil and you do the analysis that control everything, you are severely underestimating the system, the stiffness of the combined system. In other words, you have to think about this as, let's say, the normal spring here and the zone to which is attached as two springs in series, right? You know that when two springs are in series, you sum the opposite of the stiffness. So the combined stiffness, 1 over K, is equal 1 over K1, which is our coupling spring, plus 1 over K soil, right? So if you calibrate the 1 over K, which is our coupling spring, fixing the movement and therefore the effect of the stiffness in the zone, when you then relax because you analyze the model completely and embedded everything, you are essentially making the whole system much more deformable. So it is essentially wrong. It should not be done. The way I do it is actually the opposite. Since the soil is present with its constitutive model, the deformability, the shear strength, and whatnot, these springs are only needs to be seen as a contact element. They transfer the forces. That's it. In fact, they need to be significantly stiffer than the soil itself, exactly for the reason that I was mentioning during that for the series, because 1 over K is 1 over K spring plus 1 over K soil, right? So this 1 over K spring needs to be small so that the sum of the inverse is essentially equal to the stiffness of the soil, okay? I hope that this is clear. In the normal direction, therefore, use a Kn, which is significantly higher than the stiffness of the soil. And right now, there are a bunch of fish functions, but in the next version of FLAC3D, actually, we have implemented some sort of utilities that are reading the stiffness in the soil and just multiply and give the stiffness automatically to these links, right? And as far as the strength of the soil, you give a high value because you don't want the yielding. I'm not talking about 3D model, okay? I've seen some example into these for different purpose that are, these coupling spring are used for kind of a capture some sort of a flow, which is, in my opinion, is close to nonsense, but I've seen that as well. But the shear strength of the coupling spring, because you can specify a cohesion or friction angle, is also set very high because you don't want the coupling spring to yield. You want the coupling spring to and in order to exemplify this one, I have another example here that I did for a TRB presentation, in which I was asked to analyze the effect of these different components. This is a simple model, okay? So just to analyze the effect of these coupling springs on the system. And I'm using a different constitutive model for the pile, okay? So this is a soil. It could be a clay, for example. And this is actually a clay, a relatively soft soil. And what I'm doing here, I'm taking a certain range of variability of the pile in terms of stiffness of the pile, elastic modulus, and also I'm implementing a more advanced constitutive model for the pile, like the concrete model. Now, let's go into the lateral deformation. This is for zero axial force. But what you actually see that at the end of the day, once you accommodate the nonlinear behavior of the structure, even if you have a soft soil, the coupling springs are essentially marginal because you have a failure essentially of the pile because of plastic hinges. There is this idea that is always the soil failing or this stiffness of the pile somehow doesn't matter. But I can guarantee you, having seen load tests with inclinometer inside the pile, the cracking of the pile itself really changes the let's say load transfer curve in the horizontal direction, especially because of the cracking of the concrete and the change in stiffness of the concrete itself. So while we focus on this let's say, coupling springs saga, we don't even consider something that is way more important, which is the nonlinear behavior of the structure, especially after cracking. The concrete reduces significantly the stiffness. As you can see here, you get essentially half of the force available, and you get a much let's say softer response because the pile start cracking all the way up to breaking. All right. So I just wanted to emphasize this, that again, the concept is the opposite. You do not have this contact element as a PY. It has nothing to do with the PY curve. I hope that this become clear at some point. They are just contact element. Now, I mentioned that there is a distinction between the vertical and the horizontal. Okay. All that we have talked about for now is the horizontal. When you push a pile into the ground horizontally, you have a volume of reaction, which is somehow related to the diameter of the pile. Okay. As we have seen in the other numerical example, you have this volume, which could be, 1 diameter, 1.5 diameter. It tend to dissipate with depth and whatnot. But what you have a relatively large volume of soil that react to the force that we apply to the pile. When we apply a force in the vertical direction, the interaction along the shaft is a very thin layer of soil that provide the shaft resistance. Is not meter of soil around the shaft that actually react vertically. It's just a thin layer. It could be a couple of centimeters or even less, depending on where you are along the pile, that actually provide the tau, right, that react to the axial force. Now, if you try to model a couple of centimeters in a model that is 300 meters, you're just you're just wasting time because there is a scale effect. So what I'm trying to say is that the vertical interaction is much more localized and is not possible in practical examples, in practical model for design of large-scale project to chase a 20 millimeter shaft around the shaft of the pile in order to capture the vertical interaction. Here, the coupling spring are similar somehow to the T-zeta curve that you have in the L pile in vertical direction. I don't even know if this pile is that vertical direction, but doesn't matter. You get the point. So the way I do this, there is still a KS, which is the shaft stiffness, which should be higher than the typical T-zeta curve because we still have the soil. So even the vertical coupling spring still transfer a shear force into the zone. So it mobilize and react according to its stiffness. But the capacity of that spring, I related that to this the beta method. So I have a function, and now this also will become available in the next version, in which each node read the effective stress that we have in the zone, and according to a beta parameter that we can specify along, considering different pile theories that we have available. I tend to use the beta. I don't use alpha or lambda method. It is the more physically meaningful, in my opinion. But anyway, you can plug in any other value that you want. And then you convert the tau so that you can limit. So if you have a relative movement of the pile that goes over, essentially, if you mobilize the full capacity, at some point the force does not increase, so the tau does not increase anymore at that elevation, especially close to the top, in case you have a high axial force. The other aspect that I get a fair amount of question is, what are we going to do with the base? And I can show hopefully one example. Typically, you put a link at the base that represents the the connection of the last node of the pile in the vertical direction with the zone close to it. And that is, okay most of the time, but in certain cases, since the link doesn't really capture the size of the pile or the geometry of the pile, it is relatively easy to just create a shell here at the bottom of the pile, and sometime at the top as well, in certain cases, in order to capture the effect of the pile. And so this is important for two reasons. So at the base, if you put a shell and you have a high level of mobilization because you think that the force is actually going to the base, is rarely the case, because the pile should be designed to capture the interaction mostly with the shaft. And if you really rely on the base, you are socketing in something very stiff, or is a different type of pile, but mostly is going to the shaft. In any case, this can provide a better tool to capture the interaction with the base. But where I see that this trick, let's call it this way, is important is in many cases at the top. At the top, imagine that you have a ground improvement in which you have a layer, which is the LTP, for example, in which you put a bunch of geogrids. If you link the top of the pile, that is going to take, let's say, one zone, right? And then the force transfer mechanism is limited to the constitutive model that you're using for the LTP, right? So it's a more Coulomb, it has a friction angle of, I don't know, 45 degrees and stuff like that. So the force is not going to go above that. But if you put a shell that captures the size of the pile, you then at that point start creating and capturing the arching effect between the different columns or the different pile, which for ground improvement could be relevant. Okay, and I do that all the time when I'm dealing with ground improvement, because it is providing a much better. I would say, it's probably down here in this example as well. There you have it. So you see, this is a ground improvement in which these are columns for ground improvement, and these are the geogrids that are embedded into the LTP. This was the full model in which there are a bunch of structural elements, pile, geogrid, concrete panel, and so and whatnot. But what I'm trying to say is that if you don't put some kind of element that capture the size of the pile, you're not capturing correctly the interaction with the geogrid. And also, you're not being able to engage any type of arching in between the soil. I hope that this helps to clarify what are we doing with this type of coupling spring, and I'm still confused myself why this topic is so confusing. I guess it's probably our background, and we've been using a simplified method and lump the soil into a spring, and so we see that everything is a spring now. I don't know, but it's very simple. Is just a contact element. That's the bottom line. Keep in mind the distinction between the lateral and the vertical, and you should be good to go. I think that we have I've covered pretty much what I wanted to cover. We have 5-6 minutes left, or a few minutes. I don't see if there is any question or not. Is it the case to take some question?
Hey, Augusto. Yes. So if anyone has a question, please feel free to use the Q&A icon at the top of the Teams app, or just use the chat. I see that we do have a question. It's a different topic, but I think you'll be able to respond to it in the time that we have. So what is the best way to ensure that the input ground motion is applied correctly in a seismic analysis when using a compliant base?
I mean, there are different way that you can do. Is typically I prefer to extend the model, the depth of the model, all the way down to a layer that I can consider bedrock or close to it. So that at that point, I wouldn't need to do a deconvolution. Of course, if I have 2 kilometers of soft ground, I'm not going to go down 2 kilometers. But in many cases, you can push the model down to a certain level that you can consider bedrock, and then you can use the outcrop motion itself without doing any deconvolution, like you would need to do in case you cut the model to a certain depth and then you want to input the ground motion that you have from an outcrop, let's say to 20-meter depth, in order to consider that the shear wave velocity that you have at that depth is not the one that you have used, that you use when you recorded the outcrop, the outcrop signal. I'm not sure if this is answering the question, but essentially, I take the outcrop motion, convert it into shear stress or normal stress in any direction that you want, and that's it.
Great, thanks, Augusto. I just wanted to note that we did have some additional questions that were submitted. They were a little more software related. So we've pasted some responses to those in the chat. So please feel free to check out the chat for some of those responses. So does anyone else have a question or a follow-up question from Augusto's presentation? Okay, Augusto, do you process the CPT data directly inside FLAC, or do you get the main parameters outside and input them into FLAC?
It can go both ways. Recently, I developed some fish function in which I read the CPT's data directly and extract those parameters that I need. In some cases, I have the software that interpret the CPTs and give me the profile, and I export the profile of the property, like for example, the subbehavioral type or the BS, and then import that as a table and use that. It can go both ways.
Okay, very good, thank you.
While related to this topic, let me elaborate a little bit more, because in several projects, we have a 3D distribution of, let's say, boreal CPTs and stuff like that. So the idea is we are using a slightly different approach in that case. What we do is through the help of Ryan, which is our guru in terms of this Rhino geometry subsurface model, we create a database inside Rhino in which we have all the properties, location of the property, whatever the interpretation is. And then we use that we build a mesh around that domain in which we have all the properties distributed in the Rhino model. And then we use some kind of interpolation schemes to try to interpret for what is possible, some sort of a spatial variability, depending on the zone size and the distance and different interpolation scheme, so that we have a 3D distribution of the property of interest.
Great, well, thank you. All right, well, thank you everybody for joining us today. Augusto, thank you very much for answering these questions, for your response and your invaluable experience and knowledge, sharing that with everyone today.
Thank you.
So
thank you.
Have a good day, everyone.